And I'm going to take the live session on the doubt clearing class for aluminum based alloys and metal matrix composites. In this week's lecture, the nucleation part was covered. So let's start with that. First of all, these are the broad topics that were discussed. The grain refinement techniques, under which the grain boundary source technique and Watt hardening method was discussed. The next two topics were homogeneous and heterogeneous nucleation. After that, or under those topics, surface free energy, volume free energy, melt inoculation, carbide boride theory, peritectic reaction. These were some small topics which were discussed. So I'm going to go through all the topics one by one. But before that, if you have any specific doubt, you can ask. If you don't have any doubt, we'll start with my PPT. So first topic was the grain refinement. Grains will grow in the form of dendrites, growing readily away from the surface of the nucleate. Solute particles can then be added, called grain refiners, which limit the growth of the dendrites. Hall patch is valid up to certain grain size, is achieved by nucleating and growing the grains, and if, it will be valid only if there is enough dislocations piled up, because for grain refinement, if the grain size is enough, if the dislocation pile up is enough, then only we can use this Hall patch equation. And there were another important thing, which is at low SFE or stacking fault energy, the dislocation movement is restricted. These all topics are interrelated, and we'll get to know how this grain refinement and these things are taking place. The result of the grain refinement is increase in toughness, as grain refinement add some strength in the material. Another thing is, okay, another thing is creep, which is another material property. It will decrease with the increase in strength. So basically, creep will increase. Creep is a temperature and time dependent deformation. As temperature increases, creep increases. So basically, the sliding between each grains, those things or dislocations increases. As a result, the creep resistance property decreases inside the material, and also it affects the fracture stress in things. So the fracture stress or the fracture toughness will increase, which is a good property, but also it is dependent upon the material application in which you are likely to apply your material of the component or the component. So there is another thing, like when we are solidifying some melted material, the solidification, how we are solidifying the material in casting or in a quenching or at the time of additive manufacturing, in which process we are solidifying the material, that is very important, and based on which we get the different shapes of grains. So there is one important grain shape, which is equiax. So it's nothing but a globular shape with uniform grain size distribution and geometry, whatever you say. So this grain refinement is important because at the time of solidification, how we are solidifying, these things really affect the type of grain we are going to get. And also in the last class, we have talked about the high angle grain boundary, low angle grain boundary. So there we saw that at the grain boundaries, the low angle grain boundaries were making some um, extra strain free new grains, which was called as nucleation. Then the high angle grain boundaries under the continuous dynamic recrystallization, the new strain free grains were created inside the old grains. So that was also acting like a grain refinement. So grain refinement means we are getting some new grains of smaller size out of our old bigger grains. So this is one thing. So in case of recrystallization, we were just applying some severe plastic deformation, and severe plastic deformation is doesn't count the melting and the solidification. It's a solidified material. We are just doing some high end rolling and forging kind of things. So there we are making new strain free grain out of the old grain. But here the thing is very different in case of this particular topic, which were covered in this way. In this case, out of the melted material we are getting the new grains, or we are just forming the new grains out of the melted material, because in melted material there is no grain, but after the melted material is solidified, which will have grain, and how the grain will look like, it will be smaller, bigger, globular in shape, columnar in shape, or dendritic in shape. How the shape will be, that depends upon how we are solidifying. So there was two topics under grain refinement. One was um, the grain boundary source theory, which was saying that grain boundary itself can give rise to new grains. The dislocations pile up, and then low angle boundary, high angle boundary, all those things are related to this type of theory. So grain boundary can itself give rise to new grains, and new dislocations, which may in turn give rise to new grains. So that is one thing of grain refinement. There were some formula discussed about it, like how much length the dislocations really need to travel to get those new grains or high angle dislocation pile up. Then the next theory was work hardening theory. In work hardening, one the theory says the distance traveled by the dislocation by grain is proportional to the size of the grain, because we have talked about it that the dislocation is nothing but extra half plane. So if this is a grain, this grain will have the lattice oriented in a particular direction. This is why this thing is called a grain. And in between them, there will be an extra half plane which is creating the dislocation. And this dislocation length we don't know, and this dislocation will move, and the solute atoms are trying to catch up. Those theories are there, but how much this dislocation can move, only up to grain boundary. So it depends upon how much bigger the grain is. If the grain is very big, the dislocation will get lot of space to move inside. But if the grain is not that much big, the dislocations will not get enough space to move inside the grain, because when it reaches the grain boundary, you can ask questions like, if it reaches the even if it reaches the grain boundary, it will cross the grain boundary, it will go in the next grain, and there it can move. But at the same time, grain boundaries are the high energy zone. For dislocations to move very easily inside grain, it needs lot more energy to overcome that barrier. So it will preferably move inside one grain, like grain specific dislocations. So for that, the distance traveled by the dislocation will be proportional to the size of the grains. So there were some other set of equations. I'm not going into that equation because equations were pretty much easy. It's just how we are deriving the Hall patch equation. So we will get to reach the Hall patch equation if the grain size is enough big and the dislocation pile up is enough big. So this was the summary about the grain refinement, uh, and the applications I have already told. So the next topic was the homogeneous and heterogeneous nucleation. So this was, up to this point, it's like we are having one grain or one microstructure. This microstructure is having this grains with differently oriented lattice structures, and out of this particular microstructure we are just deforming the thing, or just applying some external load, due to which we are just refining the grains. Means out of this old grain we are now making small grains out of it. So this is grain refinement. But what happens when we solidify the melted material during casting? For example, casting is the most commonly used known technique in mechanical and metallurgical uh, subjects or domain. So, how the final grains we can get out of such processes where we will not have that much control over the grains when it is getting solidified, because solidification time we can control, yes, but at the time of solidification of the melted material we cannot control the process. So at that time how it will react, and at that time how we can get the finer grains, or what typically we get, and by changing that how we can get the finer grains. So the next topic is homogeneous nucleation.
Ma'am, I have one question.
Yes.
Sorry for interruption.
Yes,
Uh,
yes.
Actually, you told about these two grains
Yes.
when we are discussing. So, at the grain boundary, so grain boundary is considered as a high energy zone, right?
Yes.
So, if dislocation is getting piling up, and now if this dislocation has been arranged in low energy configuration at the grain boundary, so can we say that it will act as a low energy zone?
Um, yes, low angle configuration is a low energy zone. So it's like if you are having one grain, one second. So if you are having one grain and the dislocation, a lot of dislocations are there inside the grain, and if somehow this bulging taking place inside two grain at the junction of two grain boundary, this bulging may give rise to new strain free grain. We know by rearranging, if this is a low dislocation high dislocation zone, then by arranging the dislocations by themselves they will form a new strain free grain, so that will be counted as the low energy zone. But at the same time, whenever you are, so there is the lattice mismatch, or what do I say, the orientation mismatch between the lattices between these two grains should not be that high in that case. So it's like there are two grains, okay, and the orientation of these two grains have a lot of angle. So this matlab the orientation of the lattices have mismatch in between them. The angle between these two oriented lattices are more. This is why they are high energy, high angle boundaries. So basically what happens, there are the lattices, right? And in these case the lattices are arranged like this. So now you can think there is no bond breakage, okay. So somehow if there is a lot of uh, misorientation between two lattices, it means somehow this bond or the bond between two grains are either stretched or compressed. So am I clear? Like
Yes, yes, ma'am.
there are always the bonds are present inside each lattice. So you need to be very careful about these things. You need to visualize, because the grains are oriented at a particular direction means the lattices are oriented. In between two grains there are some lattice mismatch, but still there will be bond between the atoms. If the bond is broken means there is fracture inside the material, but we are not talking about the fracture, we are talking about the grain orientation. So they are oriented at different angles. The angle, if the angle is very high, then the mismatch between their orientation is high, means the bond between these two grains are either stretched or compressed, due to which they are experiencing that high energy. This is why their high angle boundaries corresponds to the high energy zone, and low angle boundaries correspond to low energy zone. So if it's also said that if it's less than 15 degree, some books refer like if it's less than 15 degree or less than 5 degree, it will be considered as one grain only if the orientation is having that below 15-degree angle. So like that. So now your question.
Yes. Ma'am, actually, we discussed in previous class that in micro shear band
Yes.
means the two low angle configuration dislocations are interacting.
Yes.
So that means if they are interacting means at the junction they are making the bond like as you said in this diagram.
Yes.
So, if they are making the bond, so is it possible to have a equiaxial grains? Means equiaxial means actually the direction of all the lattices means they are preferring some orientations, either in any directions. So, is it possible to have this equiaxial grains because they are making high angle boundary if these two low angle configurations are getting interacted?
Yes. So what I can say is you cannot predict that things so easily because there are some in the picture, as I remember, there are some columnar grains, and those columnar grains were interacting with each other, and between due to the interaction of two low angle dislocate or boundary, the high angle boundary was produced there, and out of which new grains were producing. So at that place, you can say like two columnar grains are interacting. So there are some equiax grains, but it at the same time it also depends on which procedure you are following, because out of two columnar grains you cannot get equiax grains very easily, because equiax grains are the most preferable thing and the toughest thing to get. So it's not that much easy to get an equiax gain out of the interaction between two columnar grains.
Actually, why this doubt has created because if once we are telling like these are low angle means low angle configuration of dislocations, and again if they are interacting, they are making high angle boundaries between them. So if it is high angle boundary means actually it should means if they are interacting means it cannot be like the equiaxial no because uh, so boundary is high angle means there are low high energy zone in
Yes.
between them.
So there is a lot of mismatch between their orientations. High angle means
Yes,
na? So it's
yes.
like these columnars are low angle because they are oriented in a similar direction. These columnars are again oriented in a particular direction, so they are low angle. But when these two columnars are interacting between each other, so they are making some high angle zone. Out of that high angle zone, you will be getting some grain refinement by the high angle boundary region. But it's always not true that you'll get the equiax grains very easily.
Means ma'am we can say in between we are getting low energy configuration.
No, no, this interaction will give rise to high energy boundary.
Okay, means, but if we consider about the junction only, we are not considering this. If we are considering the interaction, then it will be a high angle boundary. But if we are considering only the junction, that the new grains are nucleating. So if they are nucleating means, we have the refinement of the grain means. Can we say that the grains are means nucleating means they are
No,
rearranging
when
themselves, like
when
at the junction.
so it's like when the high angle boundaries act to give rise to new strain free grains. So inside an old grain, if some grains are forming, they are preferably, or in the most of the cases, they are equiaxed, because out of a big region, some small regions are getting formed. So this is why they are, in most of the cases, they are equiaxed, because equiax grains are very uniform each other, and their mismatch is also like that. The high angle boundaries are making those small grains, so it will be preferably equiaxed. But about the shear bands, I'm not sure that either they are forming some equiax grains, or they are just forming new grains, which we cannot uh, like say that it will be equiaxed. But
Okay, ma'am, understood.
it's a good doubt. I'll see what
Sure, ma'am.
yes, what we can get out of the interaction between shear bands.
Sure, ma'am. Understood.
Okay, so next is I was talking about the homogeneous nucleation. So for homogeneous nucleation, first of all, homogeneous nucleation is not a common thing. It's a rare thing because homogeneous nucleation something means like wait, let me just draw. It's like out of the melted region, this is melted, and out of this melted region, without any preferable or preferential sites or out of nowhere, a nucleus is forming, which is globular in shape, like something like equiax, and without any help of anything, any inoculation or in solute atoms or anything, it's forming. So it's difficult and it's rare. So homogeneous nucleation is a rare thing. You can see homogeneous nucleation is used to describe precipitates that form at random in a perfect lattice, and true homogeneous nucleation is that independent of any lattice defect and is very rare. So homogeneous covers a lot of assumption and a lot of lot uh, like what to say, something which is not very common. So commonly what happens is there is a solid wall in the mold cavity or mold of the cavity inside the casting. In that solid wall, with the help of that wall, a nucleation will start. There will be a nucleus formed out of the melted material, and in that the dendrites may form, and due to the dendrites and then breakage in the dendrites again will act as a nucleating site, and the other material, melted material, will start to nucleate, and this is how mostly the nucleation takes place. But you can imagine now homogeneous nucleation is very rare. It's very tough again, because at the same time some surface free energy and volume free energy is also related, is also acting here. So surface free energy is like how the more the surface free energy will be increased, and out of nowhere without any help of anything, one nucleus is forming, the surface free energy is increasing, and it will not let the nucleus get bigger and bigger with time. It will also always try to minimize because it's an energy, so we never want any high energy thing. So surface energy will try to restrict the growth. At the same time, the volume free energy will try to expand. It will also increase, and in the with the interaction of with the surface free energy and the volume free energy, there will be a tug of war between these two, and in the result there will be a nucleus formed out of no help of anything. And that nucleus, if the nucleus gets a size, uh, after that size is achieved, the nucleus will grow and form the grain, or it will be called as nucleus until unless it gets that diameter or gets that size. So here the assumption is nucleus is spherical, and also out of nowhere making a spherical nucleus is very tough. Also there was one thing R star. So unless until that thing is getting the size of R star, it will not be called as nucleus. It will be called as embryo. And after the R star increases, it will be called as nucleus. So here you can see the surface free energy destabilizes the nuclei. It takes energy to make an interface. So there is no solute atom that is not melted, and with the help of that solute atom, this nucleus is forming. So there is nothing. The nucleus is forming by itself, and it needs to restrict or it needs to bear with that high surface free energy, because as the surface will increase, as the nuclei will grow, the surface energy will be more and more. At the same time, volume free energy will also increase, and this is as the volume free energy is negative in sign, so depending upon in which direction it is acting, so in between the war of these two, the nuclei will grow, and with time the graph will grow or go towards the volume free energy zone. As a result, the nuclei will grow and will be called as nucleus. So this is all about the homogeneous nucleation. But the heterogeneous nucleation is different. It's more likely, it's like more easy to understand and visualize. So there is a wall, with the help of wall, the melted material is getting some support to make this type of half circle, half circular or half spherical nucleus embryo. First embryo, then the nucleus will form by growing. So it's pretty easy. So in okay, so we have seen for aluminium Ti is added. Ti will not get melted inside the melted aluminium, and that Ti will act as the nucleating site. So there was boron as well. So there are something I'll discuss about it. But before that, we have heard about another thing, which is the dendritic growth, which was not covered in the portion in today's this week's lecture. So I thought to add that dendritic growth in today's session as well. So let's just first cover the session, the 5 lectures, videos, and the materials. Then we'll start about the dendritic arm in microstructure or dendritic growth. So there was uh, a graph like this. So this is telling us about the delta G. So the volume uh, free energy gives free energy difference between the solidified and the melted region and their interface, and that interface is very important zone, because the interface will be experiencing some force between the solid liquid, some force between the due to the liquid surface energy or solid surface energy and the volume energy. So that interface is a very critical zone, because it's often said that even this half spherical nucleus has been grown, the surface or the periphery of this nucleus is not solidified. Inside this periphery, inside this dark portion, this is solidified. The outer region is melted, it's liquid. And it's also said that this zone that I have drawn with dark red, this zone is also liquid. It also not fully solidified zone. So this is why this interface or interfacial energy that we were uh, just seeing throughout all the lectures, so it's a very critical zone, and the energies related to this zone is again very critical and important. So there was one diagram like this. There was an angle, some critical angle was also needed in each direction, some surface tension, energy, volume free energy, surface free energy, interaction interface energy was acting, and based upon which some equations were drawn, and this was shown that the volume free energy for homogeneous case, for homogeneous nucleation is more. So this is why the heterogeneous nucleation is preferred. As I said, homogeneous nucleation is always preferred, but it's not practical. At the same time, heterogeneous nucleation will give rise to some heterogeneous grains inside the material. It's not that much preferred, but it's the practical thing which really takes place inside the material. So this thing was covered up to lecture 4. Then there was on one topic, grain refinement by melt inoculation. It's nothing like we are, yes.
Ma'am, I have one doubt here.
Yes.
Actually, we discussed about the free energy,
Yes.
means the surface free energy and volume free energy. So, in case of surface free energy, means if the radius is very small, means the spherical radius is very small, so surface energy will dominate over the volume free energy. Ma'am, can you explain what this energy means actually with this diagram, in some diagram? Actually, I'm not able to understand like how this volume energy is getting decreased and surface energy is getting increased always.
So it's like if this is a small thing, if it's trying to grow, the surface area will increase. As the surface area will increase, now the surface free energy will also increase. But from inside, the volume is also increasing, and the volume will help to grow this thing. Means volume free energy is also increasing as the volume is increasing. Surface free energy is also increasing as the is increasing. But it's like the volume energy is acting from inside now, so it will help to grow the material. But the surface free energy, as the surface free energy is increasing, it will try to restrict the growth, as in the outer side of that nucleus the liquid zone is present, so that liquid will not let the nuclei grow. So this is why the surface energy is restricting the growth. It will be like, it will be restricting the growth of the nuclei, but the volume free energy is not interacting with the liquid metal, the liquid material. It's acting inside the inside the nuclei. So this is why this volume 3 will also increase, but it will help to grow the nuclei. And after some time, the surface in the interaction between surface and volume, the graph will tend to move towards the volume 1, because the nuclei will be so big then that the surface energy will be so high that the surface energy will not interact with the liquid material anymore. The liquid material will not be successful to restrict the growth of this nuclei. So this is why the nuclei will grow. It's like there is one equation between the surface and the volume free. I don't have that equation, but if we see that equation, this will be clear to you.
Ma'am, if nucleus, ma'am, if the size of the nucleus is like more than R star, so at that case, if the nuclei is bigger, so we have the more surface area that is exposed. That means this surface will always try to push the nucleus in from means if it tries to just restrict the growth of the like sphere. So at that time, why this volume free energy is getting decreased? Because volume is already increasing. Means after
It's
R
not
star also.
decreased. The volume free energy is also increasing, but as it present in the negative side of the graph, it seems like it's decreasing. It's nothing but the sign. If you remove the sign, it's also increasing. We are calling it decreasing because it's negative sign. So in negative portion, if we are going from 0 to some negative value, it's decreasing. But if we just remove the negative sign, the value is increasing, but its action is opposite to the normal action. This is why we are calling that it's decreasing. It's actually increasing because the volume is increasing now. So volume free energy will also increase.
Yeah, yes, ma'am. Understood. But what is delta G? But the net delta G is decreasing after R star. Means the free energy
Okay,
change.
so the delta G is interaction between the liquid and the solid. So liquid and the solid means the liquid which was present earlier, and the solid which is now present as in the form of nuclei. So beforehand the liquid was restricting the growth of the nuclei. But now the nuclei is so big that the volume free energy corresponds to the liquid is not that much to restrict the growth of the volume free energy of the solid or nuclei. It's like the difference is minimized. The volume free energy of the solid is not minimized.
Yes, ma'am. Understood. Yeah. Yes.
Okay. Okay. uh, the next, I was talking about the lecture 4. So yeah, the difference between the volume free energy is decreased. So but in the comparison with this volume free net volume free energy between of homogeneous and heterogeneous, homogeneous will be more because the restriction is more. In case of heterogeneous, the restriction is not that much, so this is why this is less, and which makes the preferable environment for the heterogeneous nucleus to grow. So this is why we call, like, for less net home volume free energy, the energy barrier is less, so the heterogeneous will be preferred. It will find more preferential site to grow and nucleate. So there are some formulas. So again, there is one topic, solid suspension. So it's coming under the topic of melt inoculation. So it's like when we are doing some casting, we'll be adding some solid suspension inside the melted material. The solid suspension will be such a way that it will not get melted at that high temperature. So the solid suspensions will rather act as the nucleating site. So it's like with the help of the wall of that solid suspension, the material will start nucleating. So this is why Ti is added. So the melting temperature of Ti is not that much high as is higher than aluminium. So this is why at the melting temperature of aluminium, Ti will not get melted. It will be intact in its shape, and that wall of the Ti will provide some support for the new nucleus to grow. So for Ti, we cannot add Ti as it is because titanium is also a reactive material. It can react in a reverse way. So we preferably add some aluminium titanium master alloy. So in which the titanium, so they will form some intermetallics inside it. So the intermetallics, like, it will again give rise to some new strain free grain and the grain refinement, as this titanium is giving them the support, giving the nucleus the support to grow and nucleate more and more in number. So apart from titanium, boron, zirconium, tantalum, tungsten, vanadium, niobium, these are some other elements which are commonly added, but titanium is the most effective one. So apart from binary alloys, we can also add some ternary alloys for more effective things, like for more effective grain refinement, because binary alloy will give us one preferential site as Ti. But if we are adding ternary alloy, it can provide us more than one preferential sites for the nucleus to grow and or nucleate and grow. So ternary alloy, like the aluminium, titanium and boron master alloy is added, in which TiB2 and Al3Ti are will be the two intermetallics formed. So let me just write it down. So for binary alloy, we add aluminium titanium master alloy. For ternary, we add aluminium titanium boron master alloy. So 0.01% titanium is enough for the nucleation to happen in form of the master alloy aluminum 5 Ti boron. So if we add 0.2% aluminum 5 titanium boron, it will give rise to 0.01% titanium, which is enough. Then if I am adding aluminum 5 titanium 1%, it will give rise to 0.05% titanium, which is more than 0.1%, which was enough for our nucleation to happen. Again, uh, normally as 0.01% titanium is enough for the nucleation to happen, 0.003% boron is enough for the nucleation to happen. So if we are adding some material, we need to make sure that we are adding this much titanium and boron only to the to the melted material. Otherwise it will be some reverse effect inside it. It will be so brittle that it cannot serve the application. So this is also important. It's not like titanium and boron will help in the nucleation, so I will keep adding this ternary or binary alloys as per my need, as per my choice. It's not by my choice, it's about the weight percentage I am adding. The next thing is the titanium boron ratio, which is added for the ternary alloys. So it's basically 5 or 3 in most of the time. So the next topic was the effect of time and temperature. So reaction time is also important. So as I said, the cooling rate is also important. If the cooling rate is so high, then whenever we are doing solidification from high temperature melting, the grains will nucleate. Obviously it has to solidify, so the grains will nucleate, but it will not have enough time to grow. So there will be so small grains out of this melted region. When we quickly solidify, temperature down kar diya, so quickly solidifying, there will be small grains, because the heterogeneous nucleation and the homogeneous both have taken place, but they didn't have much time or enough time to grow, so the grain size will be smaller. Grain size is smaller. So if the cooling rate is low, means we are solidifying it with low speed, then the nucleus, the nucleated new grains will time to grow. So as a result, the size of the grains will be bigger, the strength will decrease. Smaller grain give rise to more strength. Then, so as I said, for rapid cooling from high temperature, petal-like aluminides will form. Slow cooling will give rise to plate-like morphology. Slow cooling from lower temperature will give rise to blocky type grains. High temperature slow cooling will give rise to secular type, acicular type something aluminides. And low temperature slow cooling will give rise to equiax attributed to the change in interfacial energy with temperature. So ALTI3, the AL3Ti is also added, will be formed in the form of intermetallics, which will have some number of facets. So it's like we have said, like in the melted or liquid metal we have added the inoculants or the inclusions, but how the inclusions will help? So it's like the inclusions are having some faces, and how many faces they are having, depending upon that the nucleation will take place, because कुछ तो support चाहिए ना to grow, to take place, the for the nucleus to take place. So the nucleus will grow or will uh, nucleate in a particular phase. So that phase is very important. So the shape, size, geometry or morphology or topology of the face is important. At the same time, how many faces are there, that is also important for the nucleus to nucleate. So this is why there was another concept of facet. Number of facets on which aluminum can nucleate will be more for blocky type morphology. Obviously, blocky type means it will have more facet as the name suggests, and the plate like will not have that much. So yeah, it's okay. Then for heterogeneous nucleation to occur, the heterogeneous surfaces has to provide some planes where there are some little mismatch as well. So it's not like the inoculants are having a lot of facet, so lot of nucleation will happen in each facet. No, the facet should also have little mismatch with the aluminum alloy. So aluminum is FCC, but so the inoculants facets should also have a kind of FCC structure so that the lattice mismatch between the facet and the nuclei to be nucleated will be low. Then only that facet will give rise to new nucleus. So there are two things. One, number of facet. Another one is the lattice orientation. Low mismatch is needed. So that low mismatch, obviously there will be less energy to nucleate, due to which the low mismatch is always preferable. So the intermetallic morphology is important in terms of this number of facet and the relationship with the lattice orientation. So there are some example, like if we are using Al3Ti intermetallic to have the nucleation to form, 112 plane will be the preferable or preferred site for the aluminium or alpha aluminium to nucleate. Lecture 5 covered the mechanism for inoculated grain refinement. There was two theory, carbide boride theory and peritectic reaction. So peritectic means out of a solid and liquid interaction, a second phase solid is forming, which is known as peritectic reaction. And carbide boride theory is like we are adding some inoculants, which will be a carbide alloy or boride alloy, and that nucleating sites are uh, forming out of that carbide and boride uh, sites. So this was all about the 5 lectures which are covered in the last week. So if you have any doubt about this all 5 lectures, please let me know. Otherwise, I'll start with the dendritic formation.
Ma'am, I am having one doubt.
Yes,
Uh,
yes.
if if we say the rapid cooling, that means we are not getting time for the nucleation. Means
No,
if
no,
we are
we are
not getting,
getting time. Nucleation means one thing you try to understand. Nucleation means some new strain free grains are forming. But anyhow, when we are cooling, it cannot be in melted in liquid state. Now it will be solidified. It will be solidified means it will be having some grain. Grain कैसे आया? Out by nucleation only. So nucleation will take place. It will be heterogeneous or homogeneous, whatever it is, but it will not get enough time to find some preferred site and then grow, nucleate, these things to happen.
ma'am, if it is not getting some preferred site for nucleation, that means actually the grain refinement also depends on these preferential sites also, right?
Yes.
So if they are not getting some preferential sites, means if even though if they are nucleating, if we are going for higher cooling rate, but if they are not getting preferential sites, means there will be some less refinement as compared to
No,
like
no,
if we are going with.
no. It's like if this is melted, and I am doing fast cooling, the cooling rate is very high. So what will happen? If it is liquid in liquid state, it will be solidified. When it is solidified, we will see some grains. How grains are formed? Grains are formed by nucleation. Nucleation means small lattices which are oriented in one particular direction, it will be solidified or freezed. So if the inside the melting or liquid also, there will be the lattices, and the lattices will not get enough time to orient themselves and then grow, like find the neighbor lattice to grow and attach with them. These things will not take place. But how they are present inside the liquid, they will suddenly just solidify. It's like the cooling rate is high, so it will be more like homogeneous. So out of nowhere, the grains will be formed, and as the grains are forming everywhere without any help of anything, like they don't need to find the preferential sites, then nucleate. These things are not happening. So the number of grains will be more because the grain size will be lesser. Is it fine?
Okay, yes, ma'am. Now understood. Means if they are having some preferential sites, means they will get attached. Means it may have some grow. Means
Yes.
the growing of the grain will take place,
Yes.
right? Okay,
Yes.
that means what about the grain boundary area? If they have some, they are finding some preferential sites. Means this grain boundary area will decrease or increase.
ग्रेन बाउंड्री एरिया मतलब क्या होता है? This is the
Ma'am,
lattice and this is the another lattice, and the boundary between these two is the grain boundary area. So grain boundary area doesn't mean anything else like a area, particular area having some another lattice. It's like the boundary between two differently oriented lattices. It's nothing like two atoms in a particular bond in which the bond length is different than the bond length in each grains, right? So the area is increased, like the bond length may be increased, है ना? They are more stretched, so the area means that only. And they are more stretched, the area is more means the energy is more. There are high, they are making some high energy boundaries. So the grain boundaries are high energy zones. It's like that only. So just try to
okay, okay.
visualize.
Okay, okay. Now understood. Ma'am. Actually, I was understanding like the grain boundary area means if the number of grains is less means the area will be means the if the number of grains is more means the area will be more.
Okay, okay. So it's like, yeah, if there are, I am making the grains like these boxes, okay? So if I have made like this, and another grain I have made like this. Now you tell me, here the number of red lines are more rather than this one. So means the grain boundary area is more. Means number of grain, if it is increased, the number of grain boundaries will be increased. So this is why you can say like the grain boundary area is increased, right?
If there is a growth or if there is a growth of the grains means there is if there is a growth like if they are finding some preferential sites then
Yes.
they have some growth. That means we will have some bigger grain as compared to the
Yes,
rapid
yes,
cooling if
yes,
right.
yes.
Okay, okay, right,
So in
understood.
okay, so in last class, as a recap, I have talked about three things. One, sorry. So one thing was quenching, one was normal, two was normalizing, and the third one was annealing. So can you tell me the difference between these three?
Yes, I'm actually in annealing we have a fast cooling rate. No, we have a slow cooling rate. Like we have a furnace cooling, and in quenching we have a fast cooling rate. Like
Yes.
even more than normalizing. Means normalizing we are doing cooling in air, but in quenching we are cooling in presence of water or oil. So I
Yes,
think
absolutely
quenching
right.
is more faster.
So now you can think, after the heat treatment, we do this type of quenching. So after any welding technique also, when we do welding na, we have a butt joint, and in the butt joint I am just moving this torch and I am doing the welding. After the Just after the welding is done, we dip this material inside the water, so it's nothing like quenching. So the welding just have completed and I have dipped this inside the water, so it's like quenching. So the grains which were forming or nucleating and growing will be suddenly freezed when it will be dipped inside the water. So even if in the welding technique, that was that will not be melted material, something semi solidified, and I'm dipping it inside the water, so the grains will be quenched, means the grain size will be smaller. And if I am keeping this welded material in the air for longer time, the semi-solid will be solidified with time and the grains will grow with time. So the grain size of the grain will be more. It was not a good example, but just to make you understand properly, I am telling about this welding application.
Actually, yes, there is one doubt here, ma'am. So, in which case we can say that the nucleation is more favorable in fast cooling or in like in quenching or in normalizing?
So, see, one thing. Quenching is fast cooling, normalizing is air cooling, slower cooling, and the annealing is the furnace cooling, so slowest cooling. So apart from cooling, you just think about it that you are having, these are done after heat treatment. In heat treatment, we do not melt the material. We just keep the material for some times beyond the recrystallization temperature. So don't think about the heat treatment and this thing. Just think about the casting techniques. When you pour the material inside the mold, it will take some time to solidify inside the mold. Now you just think, inside the mold you have poured the liquid metal. The liquid metal is having 660 degrees centigrade for aluminium, and after you have poured the metal inside the mold, you just lock the mold, you just close the mold, lock the mold, and dip it inside a water tank. What will happen? Inside the casting, the metal will get solidified faster than normal casting, है ना? Because anyhow, if we are keeping a material lower than its melting point, and even in water dipping, you are lowering down the temperature very fast, and the lowering down value is very high. The temperature of the water is very low than the melting point of the aluminum. So you are doing some fast cooling, means the liquid metal will be cooled down or solidified very rapidly. So solidified means there will be some solidified grains. Before that, there was the lattice structures, but those were in melted position. Melted state means the distance between lattices are more. So now you are just suddenly freezing it. Suddenly freezing it means the lattices, how they are arranged, they will not care about it. They will just solidify because they don't have any other option. The temperature is not that much that they can sustain that liquid state. They will just solidify suddenly. And as solidify, the grains will be formed anyhow. So the grains will be smaller because it's not like the whole metal, the whole liquid metal is solidified. So there will be only one grain. It's not like that. Grain is nothing but a single orient. The lattices are oriented in a particular direction, that much lattice will form a grain. And the lattices inside the aluminum metal will follow the FCC crystal always. But the orientation of FCC crystals are not similar in the whole metal. They are oriented in different directions, and at that time if you are freezing the material, they will be freezed and they will be solidified, small grains will be there. So this will be called as nucleation, but there is no growth of the nucleation. They cannot find the preferred site to get and sit there and grow nucleate. So they will just nucleate, they will just form the grain in the position they were present in the liquid state. So there is a nucleation, but there is no grow. You can say that homogeneous nucleation will take place. So homogeneous nucleation doesn't require any preferential site, but heterogeneous does. So for heterogeneous, they need to find a preferential site, but for homogeneous, they do not need to. So it's not like in all over the material, only homogeneous solidification will take place. So you need to understand one thing, that is, if I am having one melted metal in this mold. This is a mold, huh? This is a rectangular mold. So this mold wall is giving the material support. It's acting. It will be acting as a inoculant. So in the mold wall, near to the mold wall, the heterogeneous nucleation will be taking place. So it will be acting as a chiller. In case of casting, it's called the chiller or chilling something, but it will be acting as a heterogeneous site for the nucleation to happen. But inside this metal, there will be some temperature gradient. As soon as this will be solidified, na, the temperature of this region and the temperature of this region will be different, and the temperature of this region will be different. So due to which there will be a temperature gradient. So the grains you'll have after solidification will be having some different structures. Like somewhere you'll be getting columnar, somewhere you'll be getting equiax, somewhere you'll be getting very refined grains, means very small grains. But it's not like they are not nucleating. They have to nucleate now, otherwise how they can form the grains? Is it okay? If you have any doubt, please
No, ma'am. Actually, it is clear. It is clear
okay.
now.
Okay.
Uh,
So
Ma'am, if we are talking about the free energy of the solid and liquid, so free energy of the solid and liquid, so the free energy of the liquid is more than the free energy of solid if the temperature is less than melting point temperature.
yes.
So, can you give some points about means
Acha.
how to understand
So
it?
let me just start the dendritic growth. Maybe then you'll understand more these things. Huh? So it's like homogeneous, heterogeneous. You have just now an idea that for homogeneous, all on a sudden one nucleus will grow inside, one nucleus will form inside the liquid state. And for heterogeneous, you need a preferential site so that it will act as a support for the nuclei to nucleate, means to form. And then the growth part is another thing. If we are keeping that material for longer time, it will grow. The nucleus will grow. Means the lattices will try to get arranged, will try to minimize their mismatch between the other lattice, other grain, so that they can form a bigger grain. So growth part is different. We are just talking about the nucleation. So dendritic arm is a very popular microstructure. You'll be often noticing inside under the microscope of the aluminum alloys. So dendrites are also uh, considered as a preferential sites for the heterogeneous nucleation. Sometimes when the dendritic arm is so long that it just gets broken down inside the melted state. So the dendrites in metals are at multi-branched crystals formed during solidification. In alloy casting, distinction is made between columnar and aqueous dendrites, which differ in growing into positive and negative temperature gradient respectively. I'll be talking about it. I'll be explaining it. Columnar grains grow at a rate determined by the constitutional undercooling of the melt at their tips. Equiax grain dendrites grow as fast as the total melt undercools permits. Pure metals cannot form equiax crystals. Since constitutional undercooling cannot occur in the absence of alloying element, the secondary dendritic arm spacing increases with time of contact between the liquid and the solid. Next is the alloys have a range of solidification temperature. So alloys are made of two, three metals or non-metals or whatever, two, three constitutional elements, due to which they do have a range of solidification temperature rather than one fixed value of solidification temperature. So this is why they have a graph like this. Some liquidus temperature, like the temperature at which the solidification will start, the solidus temperature, solidus line, which will depict the temperature at which the liquefaction starts, something like that. So there are some phases, alpha, beta phase, some phase which will have zero constituent element or very low constituent element, which is alpha phase, which is considered as the primary aluminum. Then beta phase is added, means some alloying element has been added. So the alloying element will will add the range of the solidification or liquefaction temperature. So the grains can be equaxed, columnar or dendritic. Equaxed means they are globular and uniform in shape and size, and columnar means they are just elongated grains, like columnar in shape, just elongated grains. And dendritic means they are having some dendritic arms. Dendrites are often seen in the human neurons, dendrite and axons. So using that topology only, dendritic arms are explained. Liquidius temperature is a function of composition and the distance from interface. Interface means the interface of the solid and liquid. So when you are liquefying the material, if the liquefaction is taking place at a particular direction, then this liquefaction, uh, or how should I explain? If this is one material in which this part is liquid and this part is solid, how you are doing some welding or additive manufacturing in which you are moving your energy source or heat source in a particular direction, that when you are exposing the heat source to a particular region, that portion will be liquid, but at the previous section, which was earlier liquid, has been solidified. So now there is a preferential direction of the or there is a directional solidification. At that time, the solid interface is moving and going to one from one end to another end of the liquid metal, and there is a interface between the solid and the liquid, which interface will be called as liquid. Beyond the interface, beyond this side, the material is solid, and beyond this interface the material is liquid. The interfacial temperature is also always very high, even it can be higher than the liquid temperature. Then the composition is also a function of solid liquid interface. So it's like how we are solidifying, the composition will depict that as well. So there is one diagram here, the composition and the distance from solid liquid interface, there is a graph, and there is another graph between temperature and the distance from solid liquid interface. So the composition, as the distance from solid liquid interface is increasing, the composition will decrease, or as the composition is decreasing, the distance from solid liquid interface will increase. As the temperature increases, the solid liquid or yes, as the temperature increases, or as the distance from solid liquid interface increases, the temperature increases. So let's understand from this picture. So it's the same picture like the temperature and the distance from interface. So this is telling us about the solidus, liquidus line, means the line below which the solidification starts. Liquidus line. So this is the graph for the liquidus line. and this is the graph for actual temperature. How the actual temperature is taking place inside the material at the time of that directional solidification, and this is the liquidious line. So this liquidious line is fixed for a material. We know this is the liquidious line, means this is how the temperature will change with in the relation with the distance from the interface. Means if we are dealing with a metal, so if this is the metal and solid, liquid and solid, I want to get the temperature of this region. So the temperature of this region will be dependent upon the distance from this region to the interface. So this is what it means. So there is a zone between the liquidious line and the actual temperature gradient line, which is telling us about the constitutional supercooling. Supercooling means, let's see the next diagram. So here in this diagram you can see this is the solid and this is the liquid. Somehow just imagine a hump has been created out of this solid region. Hump has been created from the solid. So this part is solid and this red portion is also solid. Somehow this was just going by a line, means if previously this much was only solidified. After some time this much is solidified. After some time this much is solidified. Means this much is solidified. And now this whole portion is solidified. Now all on a sudden somehow this hump is created, which hump is solidified. Now this hump interface will have more temperature than the liquid temperature. The temperature in this zone, if it's T1, and the temperature in this zone means the interface zone is T2, then T2 will be greater than the T1. As there are a lot of energy also acting at that position, we know na, the liquidious energy, surface energy, volume free energy, the difference between that and the interfacial energy. So in the range up to x, so what is x? We'll see in the next slide. So this interaction, up to this interaction, this much length is x. So in the range up to x, the actual temperature is below the liquidious temperature. Here you can see the actual temperature value is below the liquidious temperature value. Any protrusion forms in the interface will always be at a temperature lower than the liquidious temperature. So this protrusion is having lower temperature, but the interface is having higher temperature. Lower temperature क्यों है? Because it has been solidified, so it will be having lower temperature. If this is T3, so T3 will obviously be lesser than T1. T1 is the liquid temperature. The protrusion has been solidified somehow. As a result, they feel stable. So unless until the temperature of that protrusion is lower than the liquid temperature, it will feel stable. It will be at a stable position and doesn't melt back again. Below liquidious temperature, solid is stable. This zone, up to this zone. So the solid is stable, because beyond liquidious temperature it has to be liquid. So if some protrusion has been formed, or some hump has been formed, that hump will not be stable. It will be melted back again, because it is having more temperature than the liquidious temperature, and beyond liquidious temperature everything is liquid. You can see in the picture everything is liquid in this portion beyond this liquidious temperature, and inside this liquidious temperature the metal has started forming the nucleus, means the metal has started being solidified. So any hump will be stable. Then supercooling condition depends upon the composition. So it will be called as supercooled protrusion. Means the hump which has been created will be called as supercooled region, because This hump is actually coming in the liquid zone, but as the temperature is below liquidus temperature, it is getting stabilized, and it will not melt back again. So it is called as supercooled. This is known as constitutional supercooling. So this supercooling condition, how these humps will be created and how much will be the length and size, and how this hump will be stable, whether the hump will be stabilized or not, this things also depends upon composition, because we know the liquidus temperature is a function of composition and the distance from the interface, and the composition is also the function of the solid liquid interface. So this is why this supercooling is often known as constitutional supercooling. High temperature at interface gradient, as I said, at that interface now there will be so high temperature than the liquid that it will be a critical zone. So freezing at interface means heat of fusion is released at the interface either towards solid or towards liquid. What does it mean? Let me just clear the section. So if the hump is created, so up to the creation of the hump is clear to you?
Ma'am, what is the temperature T2? It is the temperature at the surface of the hump which is attached to the liquid.
So if this is the hump, this interface is having high temperature. This अंदर वाला portion is having T2. T2 is less than T1. Is it now okay?
Okay. Yes, ma'am.
Okay. And also if the liquid is having, if the interface is having T3, T3 will be more than T1 because of the temperature gradient. So the high temperature, so uh, as the freezing has taken place, freezing means there is a hump created which is solidified out of nowhere, means with the help of the solidified portion, but it is coming in the liquid zone. So freezing has taken place, so heat of fusion is released. Obviously heat is released, this is how the solidification has taken place. So the heat of fusion can be either towards the solid side or the liquid side. Means if there is a heat, this can be released in this side or this side. Okay. So decrease as the distance from the increase the interface decide the heat transfer direction. So it's like it can be either direction, it can be in both the direction. Whatever will be, the heat will be released like this from the interface. As I said now, the heat in the at the interface is very high at this point. So the heat will be released to get the solidification, and the heat release can be in this side or can be in this side, and the heat release curve will look like this because in both the side is having lesser temperature than the interfacial temperature. Is it clear?
Yes, ma'am.
Okay. So this is why the heat of fusion will be released at either side or both the side. So this will depict us about the undercooling or supercooling. So supercooling means if the heat is going like this, whatever I have drawn, it will be called as supercooling. If the heat is like this, going like this, means the heat is released, but it's not released because it couldn't be released because the temperature in the liquid zone is very high than the interfacial zone, then it will be called as undercooled. So that's a separate concept. Just forget about this, forget about that one, concentrate in this one, how the dendrites are forming. So to dendrite, for the dendrite to form, we have to have this condition to be satisfied, this graph, that in both the sides the heat is releasing and the curve looks like this because in both the region anyhow the temperature is lower. The solid temperature is obviously lower because the solid is solidified, but in the liquid portion also the temperature is lower than the interfacial temperature. So the crystal structure dictates the direction of the growth of any protrusion occurred in the interface, because this protrusion is also having a lattice structure. It's nothing like a grain has formed. Grain means a particularly oriented lattice structure. So this is why it will be having some direction, and depending upon that direction it will grow only. If it's not having some preferential direction, or it's not experiencing some low mismatch with the solid liquid interface, it will not grow. So it's like that. So this is one picture. You see how the heat flow is taking place. So at the first time, the heat was trying to enter into this, but as this happened, so it will now grow. So this protrusion will slowly grow like this. So how it happens, I'm going to show you by drawing. So just remember this picture. This PPT will be shared to you anyhow.
Ma'am, can I ask one question
Yes, yes, please.
related to the previous one? Ma'am, actually, in lecture, the sir said is if the cooling rate is high, we have a chance of undercooling. That means the delta Tm will be more.
Okay.
And if the delta Tm is more means we have more delta Gv.
Hmm.
So if more delta Gv means delta G star will become less and we have a nucleation.
Hmm.
So how we can relate like if we have the
See,
more undercooling means uh,
yeah.
we have a more undercooling with high cooling rate.
It's like that for high cooling rate, na, this things doesn't really take place. This dendritic formation will take place, but the amount is very less. So for undercooling, as the delta G is high, so there will be chances of having homogeneous nucleation. So the nucleus will form anyhow. So it can form without any help of anything. It will grow. It will form individually inside the melt, and this is how it's called undercooling, because no one in what? Let me just draw. If this is the melt, if this is one grain nucleated, it will be having the temperature lowered than this region, but other regions are also getting nucleated like this. Suddenly, all on a sudden, we are freezing it. So this is why the delta gv is very high. Delta gv is very high, so there will be chances of homogeneous nucleation. So at that case, this type of solidious, liquidious, this type of graph, heat, fusion, release, heat of fusion will be released, or means absorbed, or whatever. These things will not take place for rapid cooling. Rapid cooling, don't mess with the rapid cooling thing with the homogeneous and heterogeneous, because in these case you are providing sufficient time for the nucleation to happen, and along with the growth, we have not come to the growth part yet. We are just talking about the nucleation. But if you cool it down very rapidly, na, there will be no growth. There will be just nucleation only. So there will be some formation of grains, small grains. The lattices will not try to orient themselves and making some dendritic arms. So there is no such things. So this is why we are talking about the slow cooling, where we have sufficient time to occur these things, this preferential sites, finding the preferential sites, and then nucleate, and then grow some dendritic arms. The dendrites will then get broken down, and those broken parts of dendrites will again act as the preferential sites for the next nucleation to grow. These things are different than the rapid cooling thing.
But ma'am, the grain will become more stable if we have a rapid cooling. Means the
Stable.
nucleation is actually nucleation is more stable in case of rapid cooling because
So
the
how?
R star will become less.
So how R star is less?
Because yeah, if we have rapid cooling, so in this case, if delta T increases means undercooling is more.
Yes. Yes.
if undercooling is more means delta GV will become more, and delta GV is inversely proportional to delta G star.
Hmm.
So if delta G star decreases means at the lesser size, the nucleus is more stable.
Yes.
So
So
if it is more stable
how?
means more number of grains will be formed.
So rather than just mugging up the things, you just tell me what do you think by the stable grains?
Yes, I am telling about the stable grains. Means if delta GB will become more, means R star will be less.
Hmm.
Means delta G star will be less. If delta G star less means nucleus can be stable at lower size.
It's fine, but I'm just asking you, just forget about this G, delta GV, delta G star, R star, whatever. You just try to imagine what do you mean by stable grains visually. Visually, now you have an idea how the grains look like. What is actually grain? What is strain feed grain? What is the lattices? How they are very oriented? So, what do you mean by stable grains? Can you explain me with the help of the grain and the lattices and their orientation?
Ma'am, actually, I was telling about the stability of the nucleus
Okay.
which is forming.
So nucleus is nothing but a grain, na?
Yes.
So what do you mean
So
by a
actually,
stable nucleus?
means the stable nucleus means if means we require some limited size. Means above this size, only the grain can be stable and it form a new grain. So if this size will be less, means at the lesser size, if it will be stable, that means at a very low size of the grains, it will have the stability to form a new grain
Yes.
at a lesser size means.
Yes.
So yes, so that means if we have undercooling, so if delta T is more, so at that case delta GV is more and delta G star will become less, and that delta G star will have the will limit the lesser size of the grain to have a stable.
So it's like always remember the undercooling, supercooling, these things are okay you if you understand, but the high cooling rate and low cooling rate, this both are different phenomena. For so as you said na, for high cooling rate the things are going reverse way. The delta GV in this case is more or the R star is less, but at for less R star value also the grains are stabilized, the grains are stable. So you cannot relate with these things with the super high cooling rate, because for high cooling rate the things are going reverse way.
Yes, that means for high cooling rate, the T1 is greater than T3, right?
T1 where
In your diagram, in previous slide.
T1
Means
is
the graph
yes,
is
yes, for that case. But what happens is in case of high cooling rate, now these things will not also happen. Means this hump creation out of the solid interface and the liquid inter solid interface is interacting with each other, and this high yes. mm, Theoretically, if this happens, the T1 should be more than T3 in case of undercooling. Obviously, there is a reverse case of supercooling, so it should be more. The T1 should be more. So then the nucleation will form even at lower side. The grain will be stabilized even at lower side. But why I am telling, because it will not happen. This is why the phenomena for higher cooling rate and lower cooling rate are completely different.
ma'am, in this temperature, which one is liquidus temperature? Is it T3, right?
T3, okay.
Because it is the interface of solid and liquid.
Yes, T3 is the liquidious temperature.
Okay, and T2 is just solidified.
Yes, T2 is solidified. It's far beyond the liquidious temperature. and T1 is in the middle of the liquidius and solidus temperature.
Okay, so free energy of the liquid is more. Means free energy depends on the temperature you are telling, right?
I am not talking about free energy here, but if you come to the conclusion from the equation, then yes.
Okay, means if the melting temperature is less, if we are having a temperature below the melting temperature,
Yes.
so the free energy of the liquid is more than the solid. Actually, from the diagram I am telling. So, how can we relate these concepts from your point of view, ma'am, as you were discussing? This
My
diagram,
point of
yes.
view in the case of supercooling, high cooling rate or low cooling, what is
Uh,
your
in,
question?
in, yeah, in case of like okay, so take example if we are having high cooling rate.
Okay.
So if our cooling rate is high and we are cooling below melting point temperature, so actually the diagram which we have when it is shown in the lecture, delta G is negative, means GL is greater than GS.
Hmm.
So, ma'am, actually, is it depend on the cooling rate also, the GL or GS,
No,
the
no, it
magnitude
doesn't
of
depend
GS
on the
and GS?
cooling rate, but it depends on the liquidius temperature that we are holding. So it's like it doesn't depend on the time, but it depends upon the temperature. And the temperature we are providing is in less time. So this is what it affects. The cooling rate is not interfering, but the time for which we are providing that temperature is less because we are providing high cooling rate. So that is what affects that sudden change in the free energy.
So, ma'am, my question is the free energy of the liquid. Why this liquid free energy is more than solid free energy if the temperature is less than melting point temperature?
This question I really don't have the answer. I need to find the answer of this question that why the free energy of liquid is less. It's a good question. I'll get back to you.
Actually, that's why this delta G become negative, and then we have the transformation from liquid to solid phase.
Yes, it's correct. But what why we are getting lower free energy in case of liquid? That should have some other reason.
Okay.
It will be
I,
related to the if it relates to the volume, then obviously the liquids have more volume than solid because
okay.
volume free energy relates is volume free energy counts the volume, so the liquid volume is always greater than the solid volume. So this is why we can say the volume free energy of liquid is more.
Yes. Now it is understood, ma'am. Yes. But in graph, actually, okay, I think delta G is delta GV, right? In graph.
Which
I
graph?
think I had done some mistake. In lecture 3, homogeneous and heterogeneous nucleation,
This one.
sir has shown one graph. Yeah. So this delta G difference is delta GV, ma'am, or this is delta G?
Let me just check. It's
Like,
delta G. See, it's delta G means it's delta GV only. Means the volume, the energy which is related to the volume, the free energy.
okay, okay. Okay, ma'am. Actually, I misunderstood.
Okay, so
Actually,
it's
I was thinking about the total delta G, delta G surface plus delta G volume.
no, it's talking about the volume free energy of liquid and solid, and this is how it's calculating the difference between those, which is helping us in terms of the nucleation for the
Okay,
heterogeneous nucleation to form.
okay, ma'am.
Okay, now I got your question. Okay, no problem. So, dendritic arms. We were studying about the dendritic arms. So, the dendritic arms, the result somewhat looks like this picture. So at the grain, now we have a hump, right? Now this hump is having lower temperature in this side and far more low temperature in this side. So this lower temperature and the latent heat fusion release like this will help this nucleus to grow further. So it will grow. So after some times, some hump will be created like this in the solid interface. And if you think about this hump, this will having one temperature which can be denoted as Ta. This is having another temperature which is Tb. Tb is the temperature between these two humps, huh? Which is near to the solid liquid interface. So this is one hump interface in which we are having Ta temperature, and in the liquid present in between two humps is having temperature which is Tb. Now this Tb will be more than Ta or Ta will be more than Tb. So if I draw a section like this, like this. So this is A section and this is A dash section. So A dash section is having some other. So we are talking about this A dash section, the region between A and A dash. In this region, we are having two different temperature, Ta and Tb, in the interface and in the liquid. So Ta is obviously having more temperature. So it will again release the heat like this. If the hump is grown somehow, like it is having some columnar structure, na? So it has grown up to certain point. Now it is releasing the heat like this. So it will now spread its arm like this. So the result will be something like this. So is it okay for you, or I was not clear? Is it okay for you?
Uh, yes, ma'am. Yes, yes, ma'am.
So wherever the temperature is lower, it is feeling lower temperature. Now it is having less than liquidus temperature. So it will anyhow find lower temperature to solidify, and it will be stable at that place. So obviously to find that stability, it will go towards the low temperature region or the low temperature gradient. So this is how the dendrites will spread its arms. So this is how the dendrites form inside the material, and this is one broken dendritic parts, and this part will again uh, act as the nucleating site for the other alpha aluminum to grow. So these dendritic arms are made out of that aluminum alloy only. So no inoculant was added. So as a result, the mismatch between these dendritic arms and the alpha aluminum will be lesser, because these dendrites are made of the aluminum alloy only. So there will be less mismatch. So the dendritic arms, the broken down arms, will be a very good preferential site for the next nucleation to happen. So this is all about the dendritic formation. There is no other slide. So in this picture you can see the humps. So this is solidified. Here some different colors you see na. These colors are depicting different grains with different orientation. Nothing than this. And then these humps are created with different colors. It was shown, and then from humps these columnar things are created. Different colors are depicting different grain orientation, and from the columnar things these dendrites are formed, and these dendrites have grown, and there are some broken down dendrites which will again act as new nucleating site or preferential sites for the nucleation to happen. So this is all about the nucleation. I haven't covered anything about growth. Yeah, for dendritic arm I have covered the growth part as well, the growth in this direction along with this direction. But in heterogeneous and homogeneous I have talked about the nucleation only. So is it fine for you?
Yes, ma'am. Means this dendritic arm is forming, I understood, but it is growing in these directions, means like perpendicular to this. So this is
Yes.
because of the temperature gradient.
Yes.
Like
Yes.
even, okay. Like
So
T1 is less than
it's not
T3 in
like
your
it will
diagram.
always grow in the perpendicular direction, but it will grow towards the liquid region, na? So it can grow
Mm.
like this. In this picture, you can see these are growing with some angles also. We are not controlling the angle between these things. It will grow by its
Means
choice.
I am discussing about this like the structure. The hump is growing.
Okay, the
Like
hump is growing. Yes, the hump, that's what I'm telling. So this hump can grow like this also, but anyhow it will grow in the direction towards the melted zone. And the secondary dendritic arm, so this is called the primary dendritic. So this one is primary dendritic arm. One second. And this one, these things are called secondary dendritic arm. Okay. So this secondary dendritic arms will form like somewhat perpendicular. This is what you'll always see the dendrites are represented like this. So it's a popularly asked questions that why the dendrites are shown like this, like a plus sign, not a triangles, because dendrites are also having a grain. Dendrites are nothing but a grain which looks like this. So normal grains we represent with this sort of irregular shape, but something close to a circle, right? But for dendrites, we represent the dendrites like this. Why? Because of its growth. Grains can be columnar. For columnar grains, it will be kind of spreaded, elongated. For normal equiax grains, it will be more like globular, circular, spherical. But dendrites look like this because of its growth.
means ma'am along the arm side or along the liquid side. Means there is a liquid along the arm also. Means like perpendicular as well as like the hump is growing. So at that direction also we have a liquid, and at the arm side also we have a liquid. Means in both of the direction it is growing, right?
Yes, yes. Because in this portion there is solid, but here is liquid, na? There is only liquid present. So in this side of the liquid and this side of the liquid, both the side it will grow. है ना? And if somehow the dendrites is not having that much stability, it can cut off from the solid and it will just be floated inside the metal, and it will act as the preferential site for the nucleation to happen. Is it okay?
Yes, ma'am. Thank you for your explanation. I was not supposed to ask this question, but this question I already faced in one of the interview.
Okay. No, no, no problem. You ask whatever you feel. If I am able to answer, I'll. If I'm not able to answer, I'll find it out and tell you in the next class. No issue.
Actually, I was not supposed. Means I didn't go till. Means
Okay.
actually, if I will find the problem, then I will ask you.
Okay,
But I
okay.
have not found this type of question. Means I was not supposed to find, but actually somehow you replied.
Okay, okay. No
Means
problem.
actually you included dendritic in this lecture. Means it was like, yeah, it's good to understand to us.
Okay. So at the end of the lecture, when it will be done by the end of the October, I'll circulate a feedback form so that it can help me in my further PS. So you can just fill it up.
Sure, 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 ma'am.
Okay. So then if you haven't studied the all the lectures, then we can continue the previous year question answers in the next class.
Yeah, sure, ma'am.
Okay, so you just first watch or go through all the lectures. Then if you have any more doubts, just let me know. We'll discuss. We'll continue this nucleation part in the next video. However, The melt inoculation 2 part 2 will be covered in this week 8. So anyhow, we'll be discussing about more about these things. So yeah.
Yeah.
Okay,
Okay,
so
ma'am.
we
Thank
can
you.
stop
Thank you,
here.
ma'am.
Thank you. Good day. Bye.
Good night.